Okay, so the surgical microscope is very simple, no much information about it, but here we come to another device that is important and there is a lot of information to need about it, which is the keratometer. So what is the keratometer? Keratometer is, from its name, it is a device used for measurement of keratometry. And what is keratometry? It is how curved is the cornea. So if we know the knowledge of how much the curvature of the cornea is called the keratometry. And the keratometry is a device used for measuring of the anterior corneal curvature in only the central 3 millimeters, because these are the most significant in regard to the vision. So what are the information that we can gain from the keratometry? We can know the radius of curvature of the cornea. So as we said in the early beginning, that the radius of curvature is just inversely proportionate to the power of the surface. So if we have a very curved surface or largely curved surface, it will have a small radius of curvature. If we have a less curved surface, then they will have a larger radius of curvature. So if we know the radius of curvature of a curved surface, we can know the power of this surface or how much this surface is curved, and vice versa. If we know how much the surface is curved, we can know what is the radius of curvature. So this device can calculate both measures, can know how much is the radius of curvature in the central 3 millimeters, and this radius of curvature will be in millimeters, and can know the power of the refractive power of the central part of the cornea in the terms of readings or keratometry readings. And by knowing the keratometric readings of the principal meridians of the cornea, like the vertical and the horizontal, or if it is not the vertical and the horizontal, the highest power and lowest power, and by subtracting the highest power from the lowest power from the highest power, we can know the degree of corneal astigmatism. So the astigmatism of the cornea can be also measured by the keratometry, and this is in diopters. We can know the directions of the principal meridians, either they are vertical or horizontal or oblique, so we can know if this patient has with the rule astigmatism or against the rule astigmatism or oblique astigmatism, and by the distribution of the myoids, we can know if there is any corneal distortion. So what is the optical principle of the keratometry? The optical principle of the keratometry is based on the first Purkinje-Sanson image. Do you remember Purkinje-Sanson image? So these images are formed by the different refracting surface of the eye due to the reflection by different refracting surfaces of the eye. So the first Purkinje image is formed by reflection from the anterior corneal surface. So we use the principle that the anterior corneal surface acts as a convex mirror. So if we have a greater, we know that the convex mirror, from the image construction of the convex mirror, we know that the convex mirror causes a small image. So if we have a more curved, the greater the curvature of then the smaller the radius of curvature and the smaller the image, meaning that if we have the cornea which is very curved, then this will lead to that the radius of curvature will be very small and the image formed will very small as well. Again, the optical principle of the keratometry that we use the anterior surface of the cornea as a reflecting mirror. This mirror is convex, and the characters of image formed by the convex mirror that it is a virtual and a small image. So if we have more curved surface, then this more curved surface will have much smaller image and will have much smaller radius of curvature. So just to remind you of what we have said earlier about astigmatism, we said that if we have the principal meridians of the eye are all of the same power, then there will be no astigmatism because there will be of the same length. if we have one meridian, which is the greatest power meridian that is more curved, like this one, so it will be smaller. Will have a smaller radius of curvature. So this cornea has astigmatism as the vertical meridian is more powerful. And also, if we have the horizontal meridian is more powerful, this means that the horizontal meridian is more curved. This means that the more curved, the smaller the radius of curvature. So the horizontal meridian here have a smaller radius of curvature than the vertical meridian. And this difference can lead to that the patient will develop astigmatism, meaning that in this condition, the horizontal meridian will form a focus in front of the retina, while the vertical meridian will form a focus behind the retina. That's why this patient has a mixed astigmatism. So the rule or the use of the keratometry is to know how much is the horizontal surface and the vertical surface and the horizontal surface are curved. And by knowing the curvature power of each one of them in diopter, we can know the radius of curvature of each one of them. We can know the astigmatism by measuring the difference between them or calculating the difference between them. And also we can know the orientation of the astigmatism, whether it is vertical or horizontal or oblique. And this is all based on the use of the anterior surface of the cornea. So the anterior surface of the cornea acts as a convex reflecting surface. So let's just make it a reflecting surface. So the cornea as a convex mirror, so we can see the object. Like if you project an object to the cornea, you can see the image of this object. As you can see here, the image of the flower is very small because the cornea is, or the anterior surface of the cornea is a convex reflecting mirror that causes smaller image. So what do we need to know is that if we place an object in front of the anterior surface of the cornea, which acts as a convex mirror, then it will produce an image. This image is small and inside the focus. So if we have an object of known size is reflected from a known distance to the anterior corneal surface, like here, if we place an object of known size and we know the distance between the object to the cornea, then we can know the radius of curvature and we can know the power of the cornea by knowing the curvature of the cornea. So the greater, as we said, the greater the curvature, then the smaller the radius of curvature and the smaller the image. So by just knowing, or by knowing the object size, we can calculate the image size. So if we calculate the image size, we can know the radius of curvature and the power of the cornea. And also, if we have an fixed image size, we can calculate the object size. And if we calculate the object size, we can know again the radius of curvature and the power of the cornea. So how can we do this? If we have an object placed in front of the cornea, then this object will be placed at a distance which is called U small in front of the cornea. And this object will produce an image. This image is called I and placed at a distance of V small from the cornea. So as we said before, in the rule of magnification is that the image size over the object size will be equal to the image distance divided by the object distance. So, and since that this is the cornea, and this is the focus, and this is the center of curvature, since that the focus is equal the radius of curvature divided by 2, so this is the radius of curvature, and this is the f, or this is the focal length. So the focus is, or the focal length is half of the radius of curvature, or the radius of curvature is double the focal length, and we need to know what is the radius of curvature of this cornea in order to calculate the power. So we just make an assumption that the focal length, or the f, is nearly equal to the v. So if we substitute V here by the F, and the F will equal R divided by 2, so the image size divided by the object size will be equal V divided by U, so V equal F and F equal R divided by 2, so image size divided by object size will equal R divided by 2U. So in order to know the radius of curvature of the cornea, we have three variables. We have the U, or the distance of the be fixed. So in order to know the radius of curvature, we have two variables, the image size and the object size. So in order to know the radius of curvature of the cornea, we need to fixate one of them in order to and adjust the other. So we can just fixate the image size and adjust the object size to know the radius of curvature. Or we can fixate the object size and adjust the image size in order to know the radius of curvature. And this is the principle of different keratometers and how do they work. So the keratometric principle that an illuminated object is placed in front of the cornea, and the cornea here now acts as a convex mirror, so that it will produce a virtual erect image, which is about 4 millimeters behind the cornea. And since this image or this distance is fixed, we can either fixate the object size to know and adjust the image size, or fix the image size and adjust the object size in order to calculate the radius of curvature of the cornea and to know the power of the keratometric reading. This slide is very, very important, which summarize the different types of keratometry and what is the principle of each one of them. So we have three types of keratometers. We have the von Jung-Helmholtz, and we have the Javalchiot's, and the Bosch-Lamp. So these are the three main types of keratometers that we have in market, and every one of them act by different principle. So please focus with me to know what are the difference between all of them. In case of von Jung-Helmholtz, the object size is fixed, and only the image size will be the variable. So we adjust the image size in order to know the radius of curvature of the cornea, but we have only the object size is fixed. The Bosch and Lamp will be acted by the same principle. So the object size will be fixed. The object size will be fixed, and the image size will be adjusted. The one which is different from both will be the Javalchiot's. In the Javalchiot's, we adjusted the object size as the image size is fixed. So the object size is adjustable while the image size is fixed. Let's know, or let's identify this in more details. But before going through these different devices, let's know or understand an important principle which is called the doubling device. You remember when I talked about the applanation trigonometry, I told you that we use a prism in the device to split the image into two images, so that when we approximate these two images, we can know that we are on the correct power or correct intraocular pressure, so that we just approximate the images in order to that these images just touching each other. And because if we just use one image, it will be difficult to identify the correct intraocular pressure. The same thing applies here, but in a just different manner. We use doubling devices. These doubling devices in the keratometry are used to measure these doubling devices are used to divide or double the image in order to overcome or counteract any slight movement by the patient. Meaning that if the patient is sitting on the keratometer, and now we are measuring the object size or measuring the image, if the patient move a little bit, then the image also will move a little bit, and we will not reach an accurate estimation of the image size. That's why we use doubling devices that will cause doubling of the image. so that we can approximate these images, and when they are touching each other, we know that we reach the correct size. And also, if the patient move, then the images will not coincide, or the images will not be approximated, so we know that we are far from the correct reading. So this difficulty can be overcome by doubling the image seen by the examiner. If the patient moves, both the images move together, and the reading could be achieved by just aligning the two images together instead of checking a single image. This will be inaccurate. So for each device, we need to know what are the doubling device that is used. So let's start with the first one, which is called the von Young-Helmholtz keratometer. In case of von Young-Helmholtz keratometer, it uses two rotating glass plates as a doubling device. Let's see this example. If we have an object here, and as we said, through refraction through parallel plate of glass, that this will undergo refraction toward the normal, then from the glass toward the air, it will refract away from the normal, so it will cause displacement of the line. So the parallel plate of glass will cause image displacement. So this can be used, this principle can be used as a doubling device in case of von Young-Helmholtz keratometer. So in case of von Young-Helmholtz keratometer, we use two rotating glass plates. These two rotating glass plates will achieve a doubling of the image. Again, these two plates will be inclined at each other so that they will cause doubling of the image. And by adjusting the knob, then these two images will be made to be to touch each other so that we reach the correct reading. So let's see this example. These plates of glass displace the light laterally as it passes through them, giving two virtual images which are viewed through the telescope. Meaning that when we are using the von Young-Helmholtz, we can here is the circle, or here is the image of the circle, and by using the doubling device will cause that this circle change into two circles. We can call them I dash and I double dash. So in order to reach the correct image size, these two semicircles or these two circles need to be adjusted until they touch each other. If they are touching each other, we know that we reach the correct image size. So here is the optics, or here is the optical principle of the von Young-Helmholtz. Here is the patient, and here is the observer, and here is the object. This object is a circular object. That light passing from this object will project through the cornea, producing an image over the cornea. Then this image, as an observer, I will be able to see them not single, but double, because the image will be reflected through the parallel plate of glasses, which will be act as a doubling device. So they will be producing double images. Then these double images are entering into the telescopic system, so they will enter parallel and emerge parallel, and they will then enter the observer's eye. So that the observer will see two images, and then by controlling a knob, then he will approximate these images together in order to reach the correct image size, so that a reading now can be read, and this will reflect the power of this meridian, or the power of this part of the cornea, and the radius of curvature. Do you want me to repeat it again? Okay. So the radius of curvature can be calculated by the same equation. It will be the double of the object distance, which is known. So, and this is all calculated by the device, not by you. and only we have two variables, the image size and the object size. So if we fix the object size and we adjust the image size by the doubling devices, and once we reach the same or the correct image size, we can now check the reading in the keratometer, so that this reading will reflect the power of the cornea and will reflect the radius of curvature. Then we have another device which is called the Javal-Schultz keratometer. The Javal-Schultz keratometer, as any keratometer, will measure the corneal curvature and will measure the astigmatism power. So here the examiner put his eyes, and here is the scale that will calculate the power of the cornea and the radius of curvature. And here is there will be here a device, and there will be another device on the other side. They will project mirrors over the cornea, and we will know their rule now. So the Javal-Schultz keratometer has a doubling device. It has a doubling device that's called Wollaston prism. You remember Wollaston prism that we said in the first early lectures of the optics? We said that it is a prism that is made from quartz, and this material has the property of splitting the light rays, so that it has two rectangular prisms that are cemented together at the telescope. So when the light enter unpolarized through the Wollaston prism, it will be split into two polarized light rays. So we use this property in case of Javal-Schultz keratometer in order to split the image, forming it two images. So again, what is the doubling device in case of Javal-Schultz keratometer? It will be the Wollaston prism. In case of Javal-Schultz keratometer, it will be the reverse of von Jung-Helmholtz. So it will produce, or it will use, a fixed image size. So what we adjust here is the object. So this device uses a fixed image and doubling device, which is the Wollaston prism, and adjustable object size to determine the radius of curvature of the cornea. So the object size is adjusted to reach the standard image size. So here, by controlling this knob, we adjust the object size as we have a fixed image size. Again, this knob will control the object size, because in case of Javal-Schultz, we have fixed image size but adjustable object size. So what are these? If we look to this is the objective lens that will projecting toward the patient's eye. So this is the front surface of the device. And if you check the front surface of the device, you will find that there are two devices that will project an illuminated mirrors. One will be a green stepladder, and the other will be red rectangles. So these are called the keratometer mirrors. There will be a green staircase or a stepladder, and there will be a red square. Here is the critical point, that the object size is the distance between the two mirrors, which is adjusted to achieve a standard image size. So when we are controlling the knob, we are changing not the size of these mirrors, but we are changing the distance between these mirrors. And in this condition, this will be the object. So the object is to change the distance between the keratometric mirrors in order to reach the standard image size. So when they are both well aligned, this will be the image size or the standard image size. Again, this is the keratometer, and we are looking from here, and this is the one mirror, and this is the other mirror, and this is the eye of patient. Here, this mirror will project a green staircase over the surface of the cornea. This mirror will project red square or red rectangle over the surface of the cornea, and through this the joystick, we can control the distance between both of them. This distance between both of them is what will adjust the adjustable object size. And by changing it, the distance between both of them, this will change the keratometric reading here and change the radius of curvature there. And when both of them, both of the red square and the green staircase are well adjusted and well aligned, then we reach the fixed image size. Let's see an example. So we have only one red square and one green staircase, but we have, so the Wollaston prism will cause doubling of each one of them, doubling of the red square and doubling of the red green staircase. So what is the object? The object is to change to move both of them in order to just touching each other. So by moving both of the green staircase and the red one and the red square, we're changing the object size. And if we reach this orientation, then this is called the fixed image size. So this will be the correct object size. But if they are both far from each other, if the green staircase and the red are both far from each other, so we have too small object size because they are far. If we move it a lot so that they will enter each other and they are separated like this, so we mean that we are moving very long. So we are now having too large object size. And this is will be incorrect. Also, after doing this in one meridian, we need to adjust it, or we turn to rotate the joystick in order to adjust in the perpendicular meridian, so that we will know the power of greatest power, or the power of the first meridian, or the first principal meridian, and the power of the second principal meridian. Note that this is incorrect, meaning that in case of astigmatism, that the Myers will not be well aligned. So the central line of the green rectangle will not be aligned with the central line of the green staircase. This means that this cornea is irregular, or this cornea has oblique astigmatism, so that we need to adjust both of them to be well aligned, so that we know the correct axis of astigmatism. And also we need that the green staircase and the red square will be just touching each other, so that we reach the correct object size. So here is the right orientation, that the line is in the middle and the Myers are just touching each other with no overlapping. So this is not correct, because the line is not well aligned, and this is also is not correct if they are too overlapping, or if they are too away from each other. So this means that these Myers are, or these readings are full. And after alignment of the Myers, we check for the greater scale above, which will be in the millimeters for the radius of curvature, and we will check also for, for the above one for the axis of astigmatism, and the smaller one will have an upper one and lower one. The upper one will be the power of the meridian, and the lower one will be for by millimeters scale for the radius of curvature. And again, the radius of curvature can be calculated by the same equation. So we have a fixed object distance, and we have a fixed image size, but we adjusted the distance between the Myers, which is the object size. Finally, we have the third type of the keratometer, which is called the Boschen lump keratometer. So what is the Boschen lump keratometer, and what is the doubling device used here? So it is another instrument used for measuring of the keratometric reading, and the doubling device here used is a prism. So we use two prisms. These prisms has the object set to a predetermined size, so we have a fixed object size, and then the doubling device is variable, or we change the doubling device so that we change the image or displacement until they reach an exact height. So we have here a fixed object size, and we change the distance between the two doubling prisms in order to in order to reach the image size. So the image size is adjustable, but the object size here is fixed. Here is the shape of the Boson lump keratometer. So here is the optics. So the test here we have what's called test sphere. This test sphere will project light through the mirrors, and these mirrors will be present with this shape. So the mirrors in the previous device or in the Javal shots was in the form of the green staircase and the red square. But the mirrors here, in case of Boson lump, which has a fixed object size, are in the form of a disk which has four signs, 2 minus and 2 plus. So it will be a disk with 2 minus signs and 2 plus signs. So here is the object that has a fixed size. So the test sphere now will produce an image. This image will be formed like this. So this is it will produce an image through the apertures like this, and then it will go through the doubling prisms. And here are the prisms. There will be a double vertical prisms that will take this object image and cause splitting or cause doubling of this image. Let's see how this occurs. So the object has the light rays will pass from the object, and it will pass through this China disk. This China disk has four apertures. Each one of them should, if the light passing through the object passing through these mirrors, they should produce a single image of this object, which is like this. So all the four images or all the four apertures should produce last a single image like this with 2 minus and 2 plus. However, we put now the doubling prism. When the light rays pass through the doubling prism, which are the two vertical prisms, these two vertical prisms are placed over two openings only. So this opening and the image from this opening and the image from this opening will produce a single image, which is the original image. But this vertical prism will cause displacement of the image. So it will cause a vertical displacement of the image, which you should project in this mirror or project it through this opening. And the other prism will be placed over another aperture, so it will cause a displacement of the image horizontally. So again, two openings or two apertures of the Shiner disk will project to the original image. Then two doubling prisms are present over two apertures. Each one of them will cause displacement of the image. So here is the original, and here is the displacement image. So we did now doubling of the image. So this is the view through this Boson lump keratometer. This is the original image. And to know the original image, you can see inside the keratometer there is a plus sign inside the original image. So we know that this is the original image. And here is the adjustable images. So we said that in case of the Boson lump, the object size is fixed and the images are adjustable. So by the use of vertical prisms, we now cause doubling of the image or doubling of the object. So this object will produce an image. These images are now adjustable. So how can it be adjusted? By approximation. So by approximation of the vertical one, so that the minus sign overlap the minus sign, and approximating the horizontal one so that the plus sign overlap the plus sign, we now reach the correct image size. So the object size is fixed, but the image size is adjustable by just moving the mirrors until they coincide with the plus and the minus signs of the original image. And that's how we can reach the correct image size, and we now can read the number on the scale of the keratometer, so we know the refractive the keratometric reading, and we know the radius of curvature. So this is the correct orientation, and by first use the first one, or the central image, or the central circus as a circle, as a guiding circle, as this is the original image. Then we adjust the vertical one and adjust the horizontal one. So these are just wrong orientation of the images. So that's the plus and the minus sign should be aligned, and you should be on the same axis in order to reach the correct power of the keratometry. And then we read on the scale, we read the radius of curvature like this in the vertical, and we read the power of the keratometric reading either in horizontal and in vertical. How to know the axis? This, let me show you the Dr. Shadi asking how to know the axis. This will be this is the vertical and this is the horizontal. The device has the ability to rotate like this and like this. So by rotation, we can adjust the orientation of the mirrors. So you can see, as you can see here, can be oblique like this. So by just rotating the device, you can orient the mirrors obliquely, so that after they are oriented, you can read the axis, and there will be a scale for the axis. So you know, for example, it is aligned at 45 degrees. Then you rotate the keratometer on the vertical direction, so that you adjust it on the 135, and then you calculate again, you adjust the mirrors again, and you know what is the correct radius of curvature and the correct power. So this can be done for the Javal. Let's also in the Javal and shots. Let's show you the shape of the device as well. So this device again, this mirrors, this one and the other one can be oriented vertical, because this circle can be rotated on the clockwise and anti-clockwise. So you can know what is the axis. Is it clear? Yes, Javal is the one which is most common. But I have worked for both the Javal and the Bosch lamp. The Bosch lamp has a very nice video on the YouTube. If you want to have more information, or to visualize how these mirrors are working and how they are moving, you will find it very interesting if you want to know more about it. Nowadays, the advent of the keratometers, or the automated digital keratometers, have made this job much more easier. So just by click of a button, you can just calculate the axis of the keratometer and the power of the keratometric readings without the need of manually adjust it. So this is just like the use of the retinoscopy and using of the autoref. So it is just the normal evolution of the devices. So the manual keratometers are like decreasing nowadays, or the use of these devices are decreasing nowadays, because they need some level of training and the practice in order to have a good reading, and also they don't work well with irregular corneas and in corneas with the scars. So the use of recent keratometers have greatly replaced them.